So our goal here in lesson 59 is to revisit some topics or some applications and skills that we've developed in the past and apply them with logarithmic functions. All right, so one of those things that we did was implicit differentiation. If I wanted to find dy dx when I've got this implicitly defined function, ln of x times y plus 5x equals 30, okay, we can use some of the things we've been learning the last couple days to do this, all right? Now what would you propose we do first?
Split up ln of x times y.
Yeah.
Okay, now could we do it without splitting those up?
No.
Yes.
Technically we actually could. The derivative of x times y over xy would be the derivative of that ln xy. But when we did the derivative of x times y, we'd have to use what? The product rule, okay? The nice thing about rewriting this first is that then I have ln x plus ln y, and notice each of those I'm not going to need to bother with the product rule at all, okay? Now we get the same result, we just, it makes it a little bit simpler, okay? So, we have now to take the derivative on both sides. Derivative of ln of x is 1 over x. What's the derivative with respect to x of ln of y?
1 over y dy dx.
Okay. Remember, implicit differentiation, it would be the derivative times this. And really, it's just a chain rule. You could rewrite this as y prime over y. Doesn't matter. But that's how we would do that derivative. Because remember, we are taking the derivative on both sides with respect to x, not y. Okay? So then we have the derivative of 5x is 5, and the derivative of 30 is 0, because it's a constant. Okay? At this point, all that's left to do is to go ahead and solve for the dy dx. Okay? So, if I do that, I'm going to have a negative 5 minus 1 over x equals dy dx over y. I multiply both sides by the y, and I've got my dy dx equals a negative 5y minus y over x. Okay?
You just took the derivative of both sides.
I just took the derivative of both sides because, again, our goal here was to find dy dx. So you take the derivative on both sides and then solve it for the dy dx. Okay. Now, this is kind of cool too. Another thing that this can do is actually make it easier to find derivatives that would be kind of complicated. All right? Here I have this function y equals x minus 2 squared over radical x squared plus 1. If I wanted to find the derivative, I could use the quotient rule with the chain rule a couple of times and simplify. All right? If I did that, dy dx, I'd have u prime times v minus u times v prime, which would be a half x squared plus 1 to the negative half times a 2x. And that whole thing would be over the v squared. So that would be x squared plus 1 to the first power. Now, we did ones like that. That's not horrible. but there actually is a little bit of an easier way. And that is, if we were to take the natural log of both sides of this equation first, then we could actually simplify that right-hand side. And I could rewrite this as ln of y equals 2 ln of x minus 2 minus a half ln of x squared plus 1. Okay, so we expanded that log on the right-hand side. And now when we take the derivative, we've got dy dx over y equals 2 times, put the inside on the bottom, the derivative of it on the top, minus a half times x squared plus 1 on the bottom, the derivative 2x on the top. And then all we would have to do at this point is multiply both sides by y. So dy dx is 2y over x minus 2 minus, the 2's cancel, xy over x squared plus 1. Okay? Now, of course, this has both x's and y's in the derivative, but it will give us the same values that this did. Okay? The equation, though, is a little bit in a simpler form, though.
Can you go back to the...
Mm-hmm.
Thank you.
Okay? So, that's another strategy that you can use these logs for, is if you don't care if your derivative has x's and y's in it, you can go ahead and take the log of both sides first to simplify it down. Okay? Alright, so here's one new theorem that we want to look at, and that is that if I take the derivative of ln of absolute value of u, it will still equal u prime over u. We already learned the rule ln of u, the derivative is u prime over u, but even if we take the absolute value of that inside function, it's still going to be u prime over u. If you think about it, this makes sense though. Because when I was doing ln of u, what had to be true about the u?
Had to be positive.
Being positive.
Yeah, it had to be positive. It couldn't equal 0 and it couldn't be negative. Had to be positive because natural log only takes positive values. That's the domain. X has to be greater than 0. Here, though, we could take it one step further and say, even if the function itself would go to 0 or negative, as long as we force it to be positive, we'll still get the right derivative. Okay? Here's a case in point. In this case, u is cosine x. Alright, so if I were finding f prime of x, the derivative would be u prime, which the derivative of cosine is negative sine over the u. Well, let's think about that. That simplifies down to negative tangent x. Check this out, okay? If I were to sketch the cosine and the absolute value of the cosine, that would look like this, okay? It starts up here. Normally, here's 2 pi. Here is, oh, I have one too few marks. Okay. There's 2 pi. Here's pi. Here's 3 pi over 2. Here's pi over 2. And normally cosine goes like this. Down to the minute pi, hits 0 there and goes there. However, if I'm doing the absolute value, it's going to come down here, hit this,
And then jump back up.
bounce back up, come down here, hit this,
Yeah.
and look like this. Okay? Now, looking at that, where would that be not differentiable?
Pi over 2 and 3 pi over 2.
At pi over 2 and 3 pi over 2, where are the asymptotes on tangent?
Pi over 2, 3 pi over 2.
At pi over 2 and 3 pi over 2. Okay? So it's not differentiable there. The asymptotes on tangent would have been right at those points where it's not differentiable. Okay? So, kind of a cool look at that.
And it's not differential because it's like the change of direction is way too sharp, right?
Yeah, it's not a smooth curve at that point, we could say. Okay? All right, two others here, two other applications. One of the other things that we did was we showed that a particular function was a solution of a differential equation. Now remember, a differential equation is just one that includes this derivative inside of it. How did we show that something was a solution to a differential equation?
We're trying to find the derivative of the one that is given
Okay. Now why would we want to do that?
to show that it is a solution.
Okay, well, let's do that. If I did y prime, I'd have to use product rule, right? So it'd be 1 times ln x plus x times 1 over x minus 4 is the derivative of 4x. So that'd give me ln x, this is 1. 1 minus 4 is a negative 3. Now, did I show that that's a solution?
No.
No. What do I have to do here?
Make them equal to each other.
Any in the silent section?
Set them equal to each other.
Set what equal to each other?
Ln x minus 3 equals to that one. To x plus y minus x y prime.
Well, let's think about that. Ln x minus 3 equals y prime. Does this equal y prime?
No.
No, but solve that equation for y prime, and then put the ln of x minus 3 where y prime is inside.
Okay, that could work. Okay, if I solved this over here for y prime, it would be x plus y. If I add the x y prime to both sides, and then I'd have to divide by the x, I'd get y prime equal to that. Then I could set these equal to each other and see if it's actually true. Okay?
And it doesn't seem to.
There's actually a little bit of an easier way of doing this, though. And that is simply by, because the only problem with what we just looked at is that we're assuming the equation is true. We're assuming it equals 0 before we've actually proven it. Okay? So that's the only kind of downside to doing that. A little simpler way that doesn't force us to prove that or to assume that that's true is simply by substituting into the left-hand side. We have x plus y. Well, y
It's actually x times ln of x minus 4x.
yeah, y is that, okay? So I'm going to put that in. X times ln x minus 4x. There's my y.
And then minus x
times ln
ln of x.
Yeah, okay. The y prime is this, right? So let's plug that in. It was ln x minus 3.
It's true. Oh wait, hold on.
Now notice I'm not setting it equal to 0. What I want to do at this point is simplify and show that it equals 0 or doesn't in order to see if this works. But notice I don't have to assume that it's true in order to do
It's equal
this.
0.
Okay?
Oh no.
Well,
Yeah.
now all we're doing is we're simplifying. So it's x plus x, well, I have a x minus 4x, so that's a negative 3x, plus x times ln x, and then I've got to distribute here. So minus x ln x plus a 3x.
It works out well.
Well, what do you know? Okay,
Everything's done.
this cancels out that, and the negative 3x cancels out that. So this whole thing does indeed equal 0. And now we've proven that it's a solution. Okay? Now we've proven it's a solution. Okay? Does that make sense? We've done some of this in the past, but now we're actually incorporating the logs into it as well. Okay. All right, one last application, then I'm going to let you guys practice with some of these. We want to find the relative extrema of y equals ln of x squared plus 2x plus 3. When you hear relative extrema, you think derivative equal to 0, okay? Or undefined, remember? When you're finding relative extrema, you're looking for where the derivative is 0 or undefined, those critical values. So, let's find the derivative first.
Is it going to be it's going to be a chain rule, right?
Yeah.
Okay, so it's going to be 2x
Plus 2
plus
over
2
x squared
over
plus 2x plus
that whole thing.
There we go. It's u prime over u, right? So the u is that polynomial or that quadratic inside the ln. Okay? So we've got the derivative of that over the x squared plus 2x plus 3. So we've got to think about two things here. One, we have to think, where would this be undefined?
Well, if we factor it, can't we tell?
Okay? Can you factor this?
Yes? No.
Yeah.
Yeah. No.
X plus
X plus 1.
X
No.
plus 2. No.
No,
No,
X plus
no.
3.
No,
X
X plus
minus
2, X
1.
plus 1. No, it's
No.
not. No.
Ah. We're thinking of it with the 3 and 2 switched. If the 3 and 2 were switched, it would factor. Or if this were a minus 3, it would factor.
No, it's not.
This one doesn't factor. So, we're going to have to try using the quadratic formula. Okay? Now, when you do the quadratic formula, always do the b squared minus 4ac first.
But that
That
one's
will tell you if
negative,
it's
right?
factorable.
That tells you if you get real numbers or not, right?
No.
So the b squared minus 4ac
4 minus 12.
is 4 minus 12, which is negative, of course.
Makes
So
it
it's
8.
not factorable?
Yikes.
So it's not factorable, but also we're doing square root, right?
So it's undefined.
So if we're taking the square root of a negative number, we're not going to get any real values where this is undefined. Okay?
So it's always defined.
No reals. So we know that y prime is defined for all real numbers. Okay? Now, do you have to write out all this work? Not necessarily, but you do at least need to go through this mentally to make sure. Okay? So then we look further and we say, okay, well, what about y prime equals 0? So y prime equals 0 if the numerator is 0, right? A fraction is only 0 if the numerator is 0.
And it's going to happen when x is going to be equal to half.
Not a half, negative 1. 2x plus 2, not 1. Okay? Alright, so there we have that critical value. And as a result, we can plug that in to find the critical point. Okay? So the point here is the point negative 1 And then we have ln of 1 squared plus 2 times 1 plus 3.
ln of 0?
Okay?
Wait.
2 times negative 1.
Never mind.
Okay?
Yeah.
So it'd be
2.
negative 1 squared plus 2 times negative 1 plus 3. 1 minus 2 plus 3 is
2.
2.
Oh, no,
Okay?
And ln of 2 is 0.67 something.
If you remember from the other day, yeah. Okay? But here's the thing, guys. You can leave it like that. Just leave your answer as ln of 2. Now, the last thing to do here is to determine what kind of point this is. Is this a relative max, a relative min, or is it maybe even a plateau point? Okay. Yes.
Sign diagram.
Hang on a sec.
If like you ask, if this is relative extrema, it's asking for the whole derivative equal 0, right? But your bottom cannot equal 0, right?
Yeah, the bottom couldn't equal 0.
Or it's undefined.
It would be undefined
So
there.
you need to make sure the top is equal 0, but the number of the top equal 0 cannot make the bottom equal 0, right?
Correct. Yeah. Now, if both the top and the bottom are 0, that means you have a hole. And a hole won't be a max or min point.
Then
Okay.
it's still undefined, right?
Yeah, it would be undefined there. So if I double check, if I plugged in a negative 2 into my denominator, we already showed that the denominator is always going to be positive. Because it never equals 0, and if I plugged in a 0, it would be a positive. So it's got to always be positive. All right? So I just need to check my numerator. So if I plug in a negative 2 in my numerator for the derivative, I get a negative 4 plus 2, which is negative, which means my function is decreasing as I approach negative 1. So now I know negative 1 is either a plateau point or a min. So now I plug in something above negative 1. If I plug in 0, I get a positive 2/3. Okay, so now I can see my function will be increasing, which means that we have a min point at negative 1 natural log of 2. And if you look at the graph over here to the left, we can see that confirmed by the graphing utility. Okay? But that's how we would find it and prove it. Okay?
So basically nothing new.
All right. Nothing new, just doing old problems with the new functions. Okay? New functions that we're able to handle.
With the new depth of knowledge.